All right, today we're going to take a look at section 14.4, which is surface area. The last section, 14.5, which we'll get to hopefully on Friday and Monday would be our plan, is on volume. And I think, honestly, volume is simpler than surface area. But if you think about it in terms of the shapes themselves, we always see surface area coming first because we just talked about area, right? And so surface area is taking a three-dimensional shape, but just looking at all the surfaces that we've already got the formulas for. So it's more complicated in the sense that it's more work to do, but it's based on the area formulas that we've already created. All right, so that's what we're looking at today. So first of all, surface area is the number of square units needed to cover a three-dimensional surface. There are two components in surface area. There's lateral area, or sometimes called lateral surface area, and then there's the bases. Okay, so the bases are the parallel pieces on top and bottom, and this one, the picture I've got on here is a pentagonal prism. So the pentagon on top and bottom, those are the bases. And then the lateral surfaces are all of the sides around, the flat faces around. Okay, so lateral area is the sum of the areas of the lateral faces. And then the surface area itself is the sum of the lateral area and the areas of the bases, the top and bottom. And this is what makes this more complicated to work with than volume, is that you're adding up a bunch of different things. And in particular, while your lateral faces may all be the same and your bases may be the same, usually the lateral face and the base are not the same. So you have at least two distinctly different quantities to calculate, and then the adding of them together when you're done. Okay? So we're going to take a look at a very simple one first, and the simple one we're going to look at is one called a cube. So there's two pictures on here, and as we work through some of these, it's often helpful to think of these two separate pictures. The one on the left is the three-dimensional object itself, correct? The one on the right is what's called a net. If you can imagine actually having this two-dimensional shape, maybe it's made out of paper, okay, or cardboard, something hard, and you were somehow able to cut apart pieces of it so that you could lay it flat, you'd get what you have on the left-hand, the right-hand side here, the net. Okay, so the net is the two-dimensional figure if you take the piece that's three-dimensional and break it down into a two-dimensional space. Okay, so can you imagine? Sometimes it's easier to take the net and imagine how you would fold it back together to get back to the original shape. Can you picture doing that from the net to the three-dimensional object? Okay, so if you take a look at the net, or if you think about the three-dimensional cube itself, this one actually has all of the faces and the bases. They're all the same, right? What shape are they? Squares. They're squares, okay? And we aren't given a side length of what these squares are, so in general, we're just going to call the side length S. So all of these side lengths, let me write it over here. Oh, we are given one actually in the other figure. I was looking at the other one. S. I was looking at the net. So these are all S, right? All the way around. I could put S's everywhere. Man, look at all those S's. I think I've got enough of them now. There's all those S's. And if you come over here to this two-dimensional flat shape, this net, it's S on the top and it's S on the side of each square. So what's the area of each square? S squared. And what would then be the area of the 6 squares then? Yeah, 6S squared. So S squared is the area of one of the squares. There are 6 squares, so if we just multiply that area times 6, we'll have the sum of all 6 areas together. So for a cube, the surface area is 6S squared. That's friendly, and it's mostly friendly because they're all the same. So let's see what happens then if we have a prism that's more a generalized prism and not a cube. Now a cube is actually a form of a prism as well, but it's very specific. Let's say that B is the area of the prism's base. Okay, so it's capital B. And P is the perimeter of the base. So the picture that I've drawn in here has S1, S2, all the way to S5, right? So the perimeter, if you will, is S1 plus S2 all the way up to S5. Everybody with me on that? Okay, I can't seem to get my dots in there right. That's my perimeter. It's called P. H is the height of the prism. You'll see that marked over here. It says, what is the formula for the surface area of a right prism? Now, if you take a look over at the net, which is what's drawn on the right, that's probably easier to look at. Now, they're not asking you to actually find the areas of the top and bottom. They're just telling you that they're B. So we're not calculating that quantity. But we do notice that there are two of those, right? So my surface area formula will have 2 times the base area, capital B. And it's going to have, in this shape, all of these rectangles, correct? Back in chapter 11, when we first learned about these shapes, these were all rectangles then as well. So what would the area of one rectangle be? Brendan, you were wanting to tell me.
Well, it'll just be side times the height.
Right, and all the sides are the same if it's, you know, a regular shape, correct? Now, the catch is we don't really know how many sides we have. I mean, in this picture, there's 5. Agreed? But what if I didn't have a pentagon? What if it were a hexagon or a decagon or something weird like a nonagon? Right? Well, what we have is we have this side times the height. This is multiplied S1H. This side S2 times the height. For the third rectangle, we have a side 3 times the height. For the fourth rectangle, we have side 4 times the height, and for the fifth rectangle, we have side 5 times the height. Everybody agree that those are the 5 areas for this particular shape? But notice what those all have in common. The height, right? The times h part, if you will. So what would happen if I add them all together? Well, if I take S1 plus S2 plus, I'm sorry, I got my h's left out. If I have all of these added together, and like y'all just said, they all have an h in them, then what I can do is I can actually factor the h out. In other words, I don't know why I put h1 over there. Let me put just h. Here's an h in all of them, and then this is S1 plus S2 plus ... S5. But we have another name for adding all the side lengths together. That name is perimeter, and it's what we wrote at the bottom. So the lateral areas, you know, the lateral surfaces areas, when we add them together, end up being P, the perimeter, times H. So you can add up the side lengths of the base and just multiply them by h, and you'll get the area of the lateral faces, plus 2 times the area of the bases themselves. So we're going to do an example, okay? Oh, this is another formula. I take it back. It's sort of an example, but it is a formula because there's no numbers in here. We're going to find the formula for the surface area of a right rectangular prism. So there's a couple of ways we could do this. What I'd like for us to do is I'd like for us to do it with that last formula, just so you can see it works, and then we'll do it sort of a different perspective of how you're maybe more used to seeing it. Because this is a shape that you're similar or you're familiar with, it makes it a little bit more natural to do something different than use that last formula. But I want to show you the last formula works. So the last formula said that the total area should be twice the base areas, we'll figure those out, plus the perimeter times the height. Right? That's the formula from the last slide. Well, 2 times the bases. Well, the base would be usually we consider at the top and the bottom. So the base is this piece up here on top, and the piece on bottom. So what is the area of the top or the bottom? LW. Does everybody agree with that? LW. They're rectangles on the top and bottom. One of the dimension of the rectangle is L, and the other dimension on the rectangle is W. Now we're going to do the perimeter. So what is the perimeter of this object? So we have to look at the base. What's the perimeter of the base? Yeah, it's 2L plus 2W, because on the base I have this L, I have this W, this one would be an L back here, and this one would be a W. So the 4 side lengths themselves would be 2 L's and 2 W's. And then we would multiply that by the height, right? So this is the formula. The formula you probably were more expecting it to look like was this: 2LW plus 2LH plus 2, oops, I didn't get that written there right, I'm sorry, that was a W. 2WH. Okay, so that's doing it from the last, the last slide's perspective. Probably not how you would have thought about this one because it is just a rectangular prism. And a right rectangular prism is easy enough to look at the actual shape and to calculate the three different sides that are going on, faces. So if we looked at, we already did the top and the bottom, right? So there's two of the rectangles that are length times width. Let's look at the right-hand side now. What is the shape on the right-hand side? Sorry, I got too much going on this picture. I gotta start over. Yeah, it's a rectangle right here. And how do you find the area of a rectangle? Multiply the two side lengths, and this one's HW, right? And there's two of them. There's one on the right-hand side and there's one on the left-hand side. So there's two of those. So there's two LWs. And then the piece that I haven't done is the front and the back, if you will. So, oh, did I say the wrong thing? I did. Yeah, on the picture it's HWs. Thank you. The front side, sort of the piece that's nearest to us when we look at it, has a length of L and a length of H, correct? Those are the two lengths of the two sides. And again, there's one that's the closest to us, and then there's one that's at the far back that's almost dotted in, and you can't see most of it. So this piece then on the front would be, let me get them right, LH, correct? And there's two of them because there's one on the front and there's one on the back. Okay. Of course, it's the same thing, right? We're just thinking about it from a slightly different perspective on the two different ways to do it. All right, the next one is a cylinder. So a cylinder is fun because in a cylinder we don't even have all polygons. And not only that, but the lateral area isn't a polygon. They aren't rectangles either, right? The last ones we were looking at were rectangles. So imagine cutting apart an aluminum can or the soup label or something like that on a can. If you were to cut the soup label off of the can and you rolled it out flat, what shape would you get for the paper? It would be a rectangle. And the part that's on top and the part that's on bottom, of course, are circles. So when we're looking at this, what we really have, as we're looking for the surface area, I'm just going to write it out sort of in words, is we have two circles plus a rectangle. Are you with me? And that's why you get the picture on the right-hand side of the net that looks like two circles and a rectangle. So we have to have the area of each of these, right? So this isn't really the surface area. This is more of the object itself. And we're going to calculate the formula for the surface area in a minute. And my object is two circles and a rectangle. The surface area for this object then, well, what's the area of a circle?
2 pi.
That's close. That's circumference.
Pi times radius squared.
Pi r squared. And why do I have the 2 here in the front? Because I have two circles, one on top and one on bottom. So pi r squared is the area formula. The 2 in the front is because I have two circles, one on top, one on bottom. Okay, now we got to take a look at the formula for the rectangle itself. So rectangles, of course, are length times width. And we know that one of those dimensions is simply the height of our can or whatever we have, our object, correct? The other one is going to be the length of the side, but the side actually came from doing the circular base all the way around. Well, that's called the circumference, right? So this length right here is the same as this length right here. And the circumference of a circle is 2 pi r. And then, oops, I put h, 2 pi r. And then we have that times the height of the rectangle itself, which is h. So we end up with pi r squared plus 2 pi r h for the surface area of a cone, of a cylinder, excuse me. So now we're going to do one, and it actually really is a soup can. Okay, so you need to be really careful when you're looking at the problems themselves about what they're asking. This says, a soup can has diameter 2 5/8 inch and a height of 4 inch. What is the area of the paper needed for the can's label if the label is to cover the entire lateral surface area? So if we're looking back at this formula, do we need to use this whole formula?
No.
No. What part do we need to use to answer the question?
Under 2 pi r
Yeah,
times.
just the second part, right? Because this first part was the circle part of the top and the bottom of, in this case, a soup can. But that's not where paper is on a soup can, agreed? The second part is the paper part that wrapped around. So what this problem is really asking me to find is just the area of this rectangle. Correct? So as I'm looking at this problem, I need to make sure that that's what I'm finding. So I need to find, in this case, I'm going to write down it's LA. This is, or you could LSA if you'd like. It's just the lateral surface area of this particular object, not the whole surface area. And it should be 2 pi RH, according to the formula that we did, and we talked through why. So what are we going to get for R, and what do we get for H?
R is 2 pi x. No, it's 2 pi x.
Ah, so this value that they gave us right here is actually called the diameter, but we can use this to find the radius. We have to divide it by 2, correct? So if you take 2 5/8 and you divide it by 2, you need to figure out what you have. Well, you can do it piecewise if you want. 2 divided by 2 is 1. Agreed? What is 5/8 divided by 2? 5/16. Good job, Madison. So what you would want to remember, this is proportional statistical reasoning, is that dividing by 2 is the same as multiplying by 1/2. So that's where it comes from. That's where the 5/16 comes from. Okay? Now, I'm going to write it in there that way, but it might be more helpful in a moment here to convert that into a decimal, or your calculator will do it for you. Right? This is 1 5/16. What's my height? 4. All right, so you need 2 times pi times 1 5/16 times 4. If you clean this up, so I'll clean it up with you, you might notice that, let me use this color, that this 4 and this 16 will reduce. In fact, what we might want to do even is to change this into a mixed number. So if we multiply 1 times 16, we get 16 plus 5. What's 16 plus 5? 21 over 16. And then I can take the 4 and reduce it with the 16 to give me a 4 on bottom. I can also reduce the 4 with this 2 to give me a 2 on bottom. You don't have to do this, but it might make the entry into your calculator a little bit cleaner. This is 21 pi over 2. So the actual answer, like in exact form, would be 21 pi over 2, or you could say 10.5 pi. But if you said that to the manufacturer at the soup company, they'd look at you like you just stepped off somewhere, I don't even know, Math Planet or something. And they would say, well, what is that as, you know, an actual measurement? Like if I measured on a ruler, what would I measure out, basically? So if we do that, and we put our calculator either 10.5 pi or the 21 pi over 2, or some version of the one above, what do we get for an approximation of this?
32.99.
Yeah, we've been using 2 decimals, so we'll continue to do that, 32.99. And I do need units. What were the units on this particular problem?
Inches.
Okay, is it going to be inches?
Square.
It's going to be square inches because we're working with the quantity area, correct? And area is square inches. And if you think about it, it makes sense because what we did here is we multiplied inches here by inches here, right? Multiply inches by inches, you get square inches. Okay, but we don't just have this object. We have a couple more we're going to look at. Pyramids. Okay, so a pyramid is distinctly different than the other 2 objects that we've looked at. We've looked at prisms and cylinders. And in prisms and cylinders, we have bases on the top and the bottom, and we have something going on around it, correct? On a pyramid, we only have one base. And then we have these shapes along the sides. And what are the shapes along the sides of pyramids? They're triangles. So we're going to have a bunch of triangles that we're working with. And we're going to have whatever the base is on bottom, whether it's a square or a pentagon or, you know, a decagon, whatever it is on bottom. So if you take a look at the surface area on this one, the first thing to remember or to notice, kind of like the other one, is that we have some kind of a base area on bottom. And we'll call it capital B, which is terrible here because there's a letter B in the problem, but we're just going to hold our breath and pretend that we're okay with that. B is the base on bottom. Okay. Now, aside from that, we need to find all of these triangles and find their area. Now, if the areas, or if the triangles themselves are all the same, if they're congruent because we're dealing with a regular shaped bottom, you know, it's a square or it's a regular pentagon or a regular hexagon, then all of those side lengths are the same on the bottom, which means that all the triangles are going to be congruent, and that's very friendly. Certainly wouldn't have to be true, but when it is true, that makes things nice. So let's just talk about each of these triangles individually. Notice an important fact here is that we don't really want the height of the pyramid. We want the height of the triangles on the side. And that's actually called the slant height of the pyramid. So if you take the apex, the top of the pyramid, and you go down to the perpendicular of one of the sides, that's the slant height. So it's the height of the slant. So that's the L that's marked in all of these pictures. You notice H isn't, it's not called H. Don't ask me why it's called L. I think it's going off of the second letter because S is a terrible letter to use, and we use S for side lengths a lot anyway. So I think that's why they're using it, but the slant height is labeled L. So they're not calling it H because H would actually be the apex down to the center of the base, and that's not what we have. And we will use that, but that's in chapter or section 14.5. All right, so what would the area of, we'll use this one of these triangles be? 1/2 L, because that's the height, and little b, lowercase b, because it is the length of the side of one of the base, or length of one of the base's sides. And notice we would add a whole bunch of these together, right? And if the bases were all different, so like if this were base 1, and this were base 2, and this were base 3, and this were base 4, kind of like I had side 1 up to side 5 on the last slide where we did a problem like this. And we added all these together, so we had, then they would all have a 1/2 B in them, correct? All of them be 1/2 and times, I don't mean B, L, 1/2 and an L in them. They would have a 1/2 in them because that's how you find the area of a triangle, and they would have an L in them because they all have the same slant height. So far, so good? Okay. This only works for a right pyramid as well. I don't think I have that written down on the slide. Not to worry, we're not working with oblique pyramids, but just so that you're knowing this is a right pyramid. Okay, what was I doing? Oh yeah, so they all have a 1/2 and an L in them. And then we would actually notice that they all might have, potentially have, different base heights. Base 1 plus base 2 plus all the way up to however many bases they have. Base N, we'll say for a minute. But what would happen if you added all those bases together? You get the perimeter of the base, right? It'd be the perimeter of whatever that object was on bottom. In this case, it's a square, but it certainly wouldn't have to be. So this would be 1/2 L times the perimeter of the base, but we call it P there, okay? So over here, we'd get plus 1/2 perimeter times the slant height. If all the bases are the same, you could actually write down that this is 1/2. Instead of writing perimeter, you could write the base times n, which is the number of sides. So this is the side length on the base. And this would be the number of sides. Of course, it only works if the bases are all the same, right? The base sides are all the same. That's another version of how to write this portion of it.
I mean, would it still be acceptable just doing the way that you had it up there?
Absolutely. Yeah. I just don't want you to look in the book and be like, hey, I see this other formula. Why didn't she say about this one? It's there. It's just another version of it. Okay, we're going to do an example of one. This is a real life example. I think, Olivia, you were in my office asking about your presentation. Was it you? Who was in my office asking about presentation? Miss Sally, because you were talking about application, wasn't it? Yeah, that's right. Okay. So this chapter 14 has wonderful application problems because areas, volumes, surface areas are like real life things, right? So this would be an example of a real life surface area type problem. So the basic shape of the Trans-America building in San Francisco is a right square pyramid with a height of 260 meters and a square base with a perimeter of 140 meters. The altitude of each triangular face is 261 meters. Find both the lateral area and the surface area for the Trans-America building. Okay? This is an actual physical object. Let's draw it, because I think that will help me anyway to get a picture of what's going on in my mind. So we have a square pyramid. I'm going to do my best to draw it. So it's got a square base. You have to draw it on an angle, otherwise it doesn't work. And then it comes up to the top of a pyramid like this. Okay, so far so good for everybody? It tells us the perimeter of the object at the bottom. So the perimeter of the square is what? 140. So if you really want to, could you find the side lengths of each of the sides of the square at the bottom? Sure, no problem. We could do that. We don't need to, but we could do it if we needed to, right? It'd be 35, just so you know. All right? It also tells us, let's see, what else do we have? That the height of the actual pyramid is 260 meters. Now, be careful on what they're giving you there, of course. They're giving you from the apex, where? Down to the middle right here. Whoops. Try that again. This is the height they're talking about, 260 right there. Is that a measurement that I need for my argument right here? No, it's not. If I were finding the volume of this building, I would need that one. But I don't, because the slant height is what I actually need. And that's actually really nice because it talks about the altitude of the triangular faces here. So altitude of a triangle just means height of a triangle, correct? Just another word for height of the triangle. So they do actually give me the other height that would be helpful for me to know. They give me the height of the side of the triangle, like right here. And this height, we'll call it L, is equal to 261 meters. Pictures are amazing. Even if your picture's not super accurate, it helps to visualize what's going on. Now, I do need to find the lateral area, and then in a minute I'll find the surface area. So the lateral area is the triangular pieces, correct? If you take a look at this picture, the lateral area is the part here at the end, the 1/2 PL. Well, since I'm given P and I'm given L, that's an easy calculation, correct? So I have 1/2 perimeter, which was 140, the slant height, which is 261. So what is 1/2 of 140 times 261? Is it 18,000, Catherine?
18,270
Okay, and are there units that I should include on this?
square meters.
Square meters. Okay, we're almost done. Let's find the area of the base itself. Well, the base itself was a square, and interestingly enough, a moment ago I told you what the side length was. How would you find the side length? Divide by 4, and I think I told you this was 35. 35. So how would I find the area of the base? Length times width, and they're both 35, right? So 35 times 35.
1,225.
Oops, sorry. Square meters, correct? And then that means the surface area height, or surface area of all of it would be the 18,270 plus the 1,225 for a grand total of what? 19,495 meters squared. Okay, and those actually were the two areas I was asked to find.